let's get going. We are doing the problems today so that everything up through and including the chain rule is wrapped up. And so when Tuesday comes, we're going to start the new section, which is on implicit differentiation. So, but I hear there's a little hubbub about the problems 3 and 4 on the problem set. Okay. So the directions say all problems must be justified without a calculator. Okay. That does not mean that you secretly use a calculator. Then get answers, and then put them in there and pretend like you didn't use one. So there is, we have a process that we go through, and you know the process. It's see if you can plug it in. Can't plug it in. See if you can think about what the graph looks like. That doesn't work. See if you can factor and cancel. That doesn't work. Then you see if there's any trig, special trig ones that you can use, so on. And if you go all the way through the list and things don't work, then what do you do? Then you test it numerically, okay? You're going to get tested by plugging in values that are close to that on the left side and on the right side, and use your knowledge of functions to be able to determine whether or not we've got positives or negatives, okay? If there's a denominator that's getting close to 0, then the likelihood of it being an asymptote is extremely high. So that means that you're going to want to plug in and see what happens as you get closer and closer to the number from the left and the right. You may just find yourself doing that for those 2 problems. Okay? All right. So that's that. All right, let's just start. I got the problems on the board. This is a summary. We're all good. So the deal that we have at this moment is that the functions yeah, my evaluate is wrong. Yeah. Evaluate. I think I swapped my U and my A. Yep. Okay. All right. So the secret now to doing these complex problems is the fact that you have to know all of your rules. And you then have to know when to apply them. So each one of these, I can tell, is some sort of combination of a chain rule, but then it might be also a combination of a product rule. And I see another product rule over there. So you have to you have to do enough of these. That's the whole reason why I gave you so many problems in your homework, because you have to just see and work with these so well. So here's what I would recommend. I'm doing a problem like this, and I got to find the derivative. I separate it by using parentheses to say, aha, I have 2 functions multiplied together. That means I have to do the product rule. But then, as I do the product rule, I know that when I find the derivative of each of these, that I'm going to end up having to do the chain rule. Okay? So it's one thing inside of another thing, and that's very, very common. On the AP exam, you'll have to be able to do these kinds of problems. That's they only like to give the complicated ones, just so you know. Okay? So here we go. Derivative of h using the product rule. Everybody gets to be the derivative, and everybody has to sit out once. So the derivative, I'm going to do the derivative of the sine of 2x first, which is the cosine of 2x multiplied by 2. And I think I'll accentuate my parentheses so you see what we have. This is the derivative of the sine of 2x. It's the cosine of 2x times 2. Chain rule, classic. And then this one gets brought down, so it's the cosine of 2x plus So that's the first half of the product rule. Then the first function, it sits out, so it's the sine of 2x. And then we multiply it by the derivative of the cosine of 2x, which is the negative sine of 2x multiplied by the derivative of 2x, which is 2. And that would be your first line in what the derivative is. After this, it's just algebra cleanup. So I see this, and I see 2 cosine squared of 2x, because I've got 2 of them multiplied together, so I can write it as a square. And then this one's actually going to become minus 2 sine squared 2x. And that would be final answer. Yeah?
I looked on Swivl for this one, and it said something about a double angle formula.
Yeah. The double angle formula, I'll just tell you right now that you don't have to worry about it. Okay?
So that's it, just acceptable.
Just acceptable, just like that. Double angle formula, now I'm going to get it. It's out there. You can look it up. All right, next one. This is the function is 1/4 sine squared of 2x. For convenience sake, I would rewrite it just so we know what's going on here. I'd like to see it. I'd like to visualize it like this. Okay, so it's 1/4 sine of 2x quantity squared. And then apply the chain rule. So the derivative of this is 1/4 times 2 times the sine of 2x to the first power. That's the first part. Then multiplied by the derivative of the sine of 2x, which is the cosine of 2x, times the derivative of 2x, which is 2. We keep on going down the chain. Now you can use the u's and the w's and the y's if you want to, okay, and it'll still all work out. Okay, I've seen a couple of crinkly faces on this one. Are we good with this? Okay, then we clean it up. 4 on top, 4 on the bottom. So this is really just the sine of x times the sine of 2x times the cosine of 2x. Okay? Yeah.
So, just the way I'm thinking of it, when like you take a power down, you have to leave the function the same before you can move on to the next.
Correct.
Okay, so that's a correct way to think about it.
That's the correct way to think about it. And maybe, I think it'd be maybe good for me to just demo this one with using the mechanical format. Think of this as y equals 1/4 u squared. Okay? Where u is equal to the sine of w. And w equals 2x. Can you see how this is just like the nesting dolls? Got one thing inside of another, inside of another. So if you take the derivative of each of these individually, paying attention to their letters, you'll see that this is why we do the outside dy du is equal to 1/4 times 2 times u to the first. This thing stays the same. That's why this guy right here stays sine of 2x. It's the u which is being left untouched. And then the derivative of u with respect to w is the cosine of w. Again, we leave this thing, when we're finding the derivative of this guy is untouched. And then finally, the derivative of w with respect to x is equal to 2. And then when you multiply the left sides, and then you multiply the right sides, and you plug everything in, you get we have there. This is the mechanical way that will always get you the problem. This is just kind of, I guess, an observation once you've done enough problems that you can really see it and you know what to do correctly. And that's the key, kind of the key. It's got to be correctly. Okay. All right, let's move on. Number 25. Infamous Jamie. All right. Okay, I look at this problem and I spy what? I spy product rule. This is the same as x times 1 minus x squared to the 1/2. That's the best way to view it. It's a product of one function and another function. Therefore, I got to do a product rule. But then it just so happens that in the product rule, when I find the derivative of the second function, I have to do it using the chain rule. So here we go. Y prime equals, and I'm going to work off of this thing right here. Function number 1 and function number 2. So the derivative of the x is 1. Then this guy sits out. Plus. Now the x sits out, and then now we do the derivative of the second function. So this is a chain rule. It's like u to the 1/2. So it's 1/2 times 1 minus x squared to the 1/2 minus 1 multiplied by the derivative of 1 minus x squared, which is negative 2x. You have to do so many of these that it just becomes natural as to what to do. It's the only way you can really get there. Okay, so then we clean it up. This is the square root of 1 minus x squared minus x times x, that's x squared. 2 and a negative 2, a 2 on top, 2 on the bottom, those are going to cancel. And this is 1/2 minus 1, so it's a negative 1/2. So I'm going to write this as x squared over the square root of 1 minus x squared. Look at each part of it. Yes?
I'm confused as to where you got x squared from. You know, for the x times
Yeah. This x, and this x. Remember, each one of these are multiplications. So this x times this x gives you the x squared. This is negative 2 over 1. So it's a negative 2 on top, 2 on the bottom, so those cancel. And the minus is what I brought here. And remember, it's not subtraction of x. It's minus that product. Okay? But that answer might not be what you saw in the back of the book. So just make sure that you know how to do this. So we have a common denominator of 1 minus square root of x, which is what we want. So we're going to multiply the top and the bottom by the square root of 1 minus x squared over the square root of 1 minus x squared. Okay. And what this gives us then, multiply this times this, you get 1 minus x squared over the square root of 1 minus x squared minus x squared over the square root of 1 minus x squared. And then now, anytime we have denominators the same, we can subtract the numerators here. So it's 1 minus x squared, which is 1 minus 2x squared over square root of 1 minus x squared. Right? Common denominator, it's all just fractions. So This is important. I can definitely see on the EP exam this being a multiple choice question. This is a classic question that they would ask. And they would have this as one of the responses. They would not have this one, the one that I had up here. Okay, so you got to be able to do that final algebra step to get it good. Alrighty, let's move on. I'm going to set this one up a little bit better. We have to evaluate this one at this point. So that's how this one is different. So this is y prime is equal to, let me rewrite it. I'm going to rewrite it first. Y is equal to x to the negative 1 plus cosine of x to the 1/2. Putting it in a form that makes it just that much easier to then find the derivative. So y prime is equal to negative 1 times x to the negative 2. That's your basic power rule in action. And then here's a chain rule. 1/2 times the cosine of x to the negative 1/2 multiplied by the derivative of the cosine, which is negative sine of x. Okay. So, well, what does this give us? This gives me negative 1 over x squared. This gives me, let's see, minus sine of x is on the top still. Bottom has 2 times the square root of the cosine of x. And this is my y prime. Okay, but that's not the final answer because we have to evaluate it when x equals pi over 2. So, here we go. I gotta tell you something funny. I was showing Mrs. Rosing the videos, and I was kneeled down like this. And so on the thing, she says, "How come you're so short?" It just looks like I'm like a midget or something. It's just funny. Okay, so negative 1 over pi over 2 squared minus the sine of pi over 2 over 2 square roots of the cosine of pi over 2. Okay. So let's see what we got here. This is negative 1 over pi squared over 4 minus, what's the sine of pi over 2? You guys fail. 2 times, what's the square root of cosine of pi? What's the cosine of pi over 2? 0. This right here, the whole world blows up, right? So it's whatever this one is, by the way, it'd be negative 4 over pi squared. Okay, minus undefined. And if anytime you subtract an undefined, the whole thing turns undefined. What does that mean?
We should put that on the dead notes and make it do it.
Yeah, that's what we're going to do.
Are we really?
Yeah. So we're going to come back to that one. We're going to find out what that's doing. Okay? And so let's finish this one. So sine of x squared, but we're going to find the second derivative. So here we go. So first derivative, f prime of x is, this is like the sine of u, okay, where u is x squared. So this is, the derivative is the cosine of x squared times 2x. That first step should be a no-brainer for everybody here. What's the derivative of the sine of x squared? But now we got to treat this as a product rule. So the second derivative, this is my first function, this is my second function, and they're multiplied together. So here we go. The derivative of cosine of x squared is the negative sine of x squared times 2x. That's the derivative of this one. Then we multiply it by the second one, because that one's sitting out, plus, this time the first one sits out, cosine of x squared, and then we multiply by the derivative of the 2x, which is 2. Is this helping that we're doing these? Okay, this is, all right. So what does this become? Well, I by 4x squared sine of x squared plus 2 cosine of x squared. And by the way, if you are destined to take out a number like a 2, okay, you can do that as long as you leave it there. Okay? You're not allowed to just take it away. Okay? So, or something that's like that. I think I should leave it on Lindsay today. She's kind of in a sassy mood.
I'll draw a sign like help us Stephanie.
It's a Superman emblem. No, this is not the function. This is where we're headed next.
Okay.
This is where we're headed next.
That's a good part. That's not a function.
So, the thing about this is what we're doing on Tuesday. What's different about this thing than what we've done before?
Not a function.
Not a function. If it's not a function, what's it called?
Not a function.
It's a set of it's a set of coordinates, which is a relation. Okay? A relation. And so if you play with the coefficients here, you get lots of fun stuff. Okay? And so this is the function.
Me too.
So anyway, okay.
Just take it.
All right. I want.
I have no idea. I walked into that class like, I'm done. I don't want to do this anymore. I hated that class. I took chem honors and Latin this year.
Okay, here we go.
Yeah, I hated that class.
So this is 1 over x. This is 1 over x plus the square root of the cosine of x. This is what the graph of it looks like. Now, where did we want it?
Negative 4 over pi squared.
Pi over 2. All right. What's pi over 2? What's pi over 2? Where's pi over 2 here?
Less than
Very
1.
roughly 1.5.
1 point what?
Very roughly 1.5.
Divided by 2.
Yeah.
1.
Yes.
1.57.
Okay. So what we have here is
1.57.
now they told us this was the point. So we're gonna just validate that quickly because it can't be in one of these spaces where there isn't a point because they're telling us that there's a point here. You see? So is there a derivative if there's no point? No. You can't draw a line tangent to something that doesn't exist. So what I'm going to do is I'm going to take this original function and let's just plug in pi over 2 and let's see what we get out of this. So it's 1 over pi over 2 plus the square root of the cosine of pi over 2. And if our luck is on our side, the answer should be 2 over pi, because that's what they told us it's supposed to be. Okay, 1 over pi over 2 is 2 over pi, plus, what's the cosine of pi over 2? 0. So, that means that 2 over pi is the point. F of pi over 2 is equal to 2 over pi. So that means it's this point right here. It's not a cusp because it doesn't have the sharp turn to turn to. Okay? So this is actually one that we have not talked about yet. If I draw the line tangent to this, okay, at this point, the line tangent to the curve is a vertical line. And the slope of a vertical line is undefined. So we have a slope tangent to this curve at that point. However, it's a vertical line, and therefore the derivative does not exist. That make sense? All right. I want to see.
I guess I did. Why? That one makes a lot of this one smells good. That one smells bad. Yeah, that was. I know what you're doing. Which one? Hey, that's
Points from there to there.
Okay. So, what is the deal? We see that this is at pi over 2. Any guesses as to what this value is?
I would guess 3 pi over 2.
3 pi over 2 is the correct answer. Okay? And so this is where pi is. This is where 2 pi is. This, of course, is where 0 is. So how come there's no graph in between those sections? Can't have the square root of a negative, and the cosine of x is under the square root. So for all of the points that are in the, and now this is how we can see it: first quadrant, second quadrant, third quadrant, fourth quadrant. For everybody in the second and third quadrants, cosine is negative, therefore there is no graph.
Do people ever graph imaginary numbers?
You graph imaginary numbers on a complex plane, and you get fractals. You get these things.
That's why fractals. It's called fractals.
Because
I think it's the one directed.
the Julia set and the Mandelbrot set are the two most famous fractal sets. And so let me give you a quick background about how to graph an imaginary number. Okay? So in our normal real world, we use x and y are both real numbers, and we plot a point. No problem for 2. Okay? Piece of cake. This goes back 100 years. Julia did a lot of work with this, and he said, wait a second. The complex plane, okay, is not the same as the Cartesian coordinate plane. And what it is you graph A on this axis, B on this axis, and when you have a number like 3 plus, or I should say 4 plus 2i, then remember this, A plus BI, that was the format. This is the real number part. So this is the real number axis. The B is the imaginary. And what happens if you plot 4, 2 on the complex plane, which is a combination of the real and imaginary, then it's just like plotting points on the coordinate plane. Okay? Now, you can plot the points just like you did before, and you think, okay, this is how you plot an imaginary point, imaginary number, on a coordinate plane, but just remember that this B represents the imaginary number. Okay? These fractals are really super cool. I don't know if you've ever played with them. You have the ability to zoom in on them, and when you zoom in, all of a sudden the shapes start recreating themselves in the shapes that look like the bigger shape that you had, and you can zoom in them forever. They're infinitely zoomable. Okay? It's so cool. Here's why. This is a coordinate plane that's made up of numbers. Okay? It turns out that these fractals, what we do is we take a point like this, take this number, and we put it in a function. Okay? I'll make up a function. We'll call it big F for my function. And I'm going to plug in a number which is going to be my A plus BI. Okay, I'm going to plug in that complex number. So I'll just say that it's C. Okay, and if I say C squared plus Z, or I'll put K because it's just a constant. This is a complex number. I'm just going to simply square the number, and then I'm going to add some constant. Super easy. Take it, plug it in. Okay, square it, add a number, and you get an answer. Okay, but this is what they do with fractals. They take the answer to that, and then they plug it back in to C. And they do it again. And they do it again. And they do it again. And they watch for how fast that number goes towards infinity. Okay? If it goes really super fast, it gets one color. If it takes a little slower to get there, it gets a different color. And black ones go to 0. They don't go to infinity. And this is actually the function for the Mandelbrot set. Yeah.
Fractals class.
Did you? Don't you totally believe that all of nature is just fractal based? It's just all mathematics?
Yeah, and people say you don't use math.
Yeah, I know.
Let's see.
I mean, why does a tree look like a tree? It's got to have some sort of formula that it's based upon.
Because I think it was 7th grade Wikidata. It was all about fractals.
Cool.
Everything concerning fractals.
Nice.
About Mandelbrot.
That's awesome.
I think we made our own fractal.